We should be recording now, right?
Yeah.
Excellent. Well, it's nice to see you guys coming out for my second lecture. I should apologize in advance. I'm a little sniffly. So I have to pause periodically and do that. So last time we talked about the problem of light trapping, and now we're going to kind of just do the exact same lecture, only everything's going to sort of be backwards. So the problem of light extraction. And if I hit the button, it should. Come on. Space bar. It's not going. There we go. So now, now we're working. All right. So a lot of these slides will look kind of familiar. You notice it's kind of just the same picture, only it's reverse all the arrows for the most part. So before, we had a thing floating in space, and we're shining light on it, and we're trying to calculate how much of that light gets trapped inside or absorbed inside of it, as opposed to reflecting away or just missing or transmitting through. Now we're just doing the opposite, where this here might represent some event that's creating photons and radiating them every which way. And some of them are going to get reabsorbed inside my material, which is presumably bad. And others are going to kind of bounce around and eventually find their way into the outside environment. So we're extracting light, and it makes a nice straightforward definition for what light extraction efficiency would look like. So you can just define it as the light that's leaving divided by the light generated inside. And we'll kind of work with that definition a little more rigorously later on, but that's the basic idea. So some applications for light extraction. Turns out this radiation by an antenna is actually a kind of light extraction problem. Anybody taken like the antenna class or advanced EM here yet? Maybe 3300, kind of, sort of. So you know about the problem of impedance matching and those sorts of issues. So that's technically a kind of light extraction problem. I'm kind of disappointed in this slide because last time it had everything from like stealth bombers to anechoic chambers as a light trapping application. But the most I can think of in the light extraction problem is just LEDs. But that's okay. It is what it is. But LEDs are just a problem if I got something that's creating light and I want to get it out into the environment to see things. So a kind of background on why LEDs are amazing. It helps to, I guess, step back and look at what we used to use in the past to make light. I guess we still kind of do. But this is the black body radiation spectrum of a 3000 Kelvin ideal black body. And this is essentially how incandescent light bulbs work. So you have a little tungsten filament here, you run an electric current through it, and it just gets hot. And if you remember Planck's law, anything that's above absolute zero is going to radiate energy, radiate photons in accordance with this black body radiation spectrum. And the shape of that curve depends on the temperature of the object. So as I go higher in temperature, that bump there gets a little further to the left and farther up. And that shaded region over there represents the visible spectrum. So that's the region of the electromagnetic spectrum to which your eyes are more or less sensitive. And you notice kind of a problem right off the bat. I'm radiating energy across this huge bandwidth, and only a tiny little fraction of it is actually in the spectrum that I'm sensitive to. So what that kind of amounts to is when I have a light bulb and I'm trying to light up a room, only about 8% of that energy is actually doing what it's supposed to. It's creating light in the spectrum that I want, and that will actually light up the room for me. And the rest of it is just kind of a glorified space heater. And when you do the math, you just integrate the area underneath the visible spectrum and divide by the total area. You find that an incandescent tungsten light bulb is at most 8% efficient, depending on how hot it is. If it's more like 2500 Kelvin, then that number goes down to maybe 4 or 5%. And that's kind of a bad efficiency value. And so this is especially concerning when you realize like a huge amount of our entire electrical grid production is devoted entirely to just making dark things light. Just lighting our homes, lighting businesses, the big shiny neon lights out in Las Vegas. A huge amount of energy is devoted entirely to that. And at most, it's only 8% efficient. So we're burning about 10 times more energy than we really need to be using in order to just light up the world. So for that reason, light-emitting diodes are becoming very, very popular. There's also things like phosphorescent light bulbs and helium mercury lamps or whatever. They all have their various emission spectra and efficiencies. But really, LEDs are kind of the holy grail of lighting for a lot of reasons. So we'll kind of see how that works here. So before, remember, we did kind of the anatomy of a solar cell, where you have a PN junction and light comes in and electrons come out. Now we're just reversing time. It's electrons and holes come in, they recombine, and then photons come out. And those photons are the things I want to create. So the physics of LEDs turns out to be kind of just the opposite of the physics of solar cells. They're just the same thing being run in reverse of each other. So what we really like about LEDs, though, is the total energy you create in the form of light depends on your band gap here. So if I have a nice direct band gap semiconductor, and I recombine an electron in a hole here, the energy difference here can either be converted into heat or it can be converted into light. And if I am very clever with my internal quantum efficiency, I can get a very strong conversion into photonic energy that way. And what's really cool is, depending on the band gap, you can also tune the color. So this is why we have very pure red, blue, and green LEDs, is because they just, through clever engineering, picked the right band gap for it. And if you're really clever, you can kind of mix the three together to get various other colors and so on, which we'll see that in a minute. But another cool advantage to LEDs is modulation. So, for example, if I want to send digital bits, I have to turn this thing physically on and off, say 1,000,000 times a second. And with LEDs, that's actually not a difficult thing to do. It's very easy to get megahertz level bandwidth with light emitting diodes, whereas if we go back with, say, incandescent bulbs, how many times can I turn this thing on and off per second? And it turns out now you're limited by the heat equation, which limits you to maybe tens of milliseconds to turn the thing on and off. And at most, you might get a few tens to a few hundred bits per second of bandwidth out of something like that. Whereas with LEDs, megabits per second is perfectly reasonable. We like LEDs. They're easy to manufacture because we're good at doing that with semiconductors. And in principle, the efficiency of an LED can get very, very high because, this next slide, I'm shoving all my photons into the visible spectrum now rather than wasting a bunch of them out there in the infrared. So this is an actual spectrum I took with one of Rajesh's spectrometers in his lab downstairs in the Warnick, or the Merrill building. This was taken with an actual just off-the-shelf flashlight from REI. And you notice you can kind of shape the spectrum however you like, depending on how clever you are with the engineering. And so this is actually kind of a standard. It's called the cool white spectrum. So you notice it's got this really strong peak here in the blue, around 450, and this big blob here in the red and the green. And when you mix them all together, it kind of creates this bluish white light. Some people might like that, some people may not. So you see variations on this theme here where you can kind of tune the color of your LEDs, which is really neat. But the key principle here is all my light is there in the visible spectrum, which means in principle I could get like 100% efficiency out of this. All the photons I'm generating are the photons I want and that I can physically see, and so they'll actually light up the room for me. So that's pretty cool. So what are the problems? What's getting in our way here? So this is kind of, this should be like a familiar model from last time where we had a solar cell and light was outside trying to get in. Now we're trying to ask what is keeping us from light, or what is keeping light from getting out? So right off the bat, you have the problem of your surface contacts are obviously going to block light and reflect it. So you want to try and minimize those. You also have the problem where when an electron and a hole recombine, you can't really control where that photon is going to go. It might go in any which direction. So I have this whole backwards direction, which is not very useful to me, which means the photon's going to have to go all the way to the back contact, bounce off, and go back to the surface again. And it may recombine in that process, depending on the attenuation properties of the material. Then you have this problem of total internal reflection, which is actually the really difficult part here. So one by one, let's say we minimize surface contacts. That's not too difficult to do. So this is kind of a fun little close-up picture of an LED dye. And you can see the little metal traces here in this very sparse grid, and they're trying very hard to minimize the blockage there. You know, in principle, I could just have a solid piece of metal, and I would have perfect diffusion of the electrons through the semiconductor, but it would just block all the light. So there's kind of a trade-off here, though, that I can't make that grid too sparse, because once that electron enters the semiconductor, it has to do this kind of Brownian walk throughout the volume of the material to find a hole and recombine and create a photon. So there's a big balancing trade-off there. But just looking at it, you can see maybe I'm only losing like 3 to 5% of my coverage there in my light extraction. So that's something we can live with. So the back contact, obviously an infinitely thick back contact would be bad, because all the light that goes down instead of up would just eventually get absorbed and do nothing for me. So you can see right off the bat, a thinner film is preferable when we're doing LEDs. But then there's still the problem of total internal reflection. So what if I put an N-reflective coating on top? And interestingly, it doesn't actually get rid of the total internal reflection. It'll get rid of the Fresnel reflection, so that's this little arrow here. It'll deal with this reflection, but if I'm outside of that escape cone, it won't matter whether or not I have an N-reflective coating on top. So I might help it a little bit, but I still have that escape cone problem I have to deal with. So this turns out to be the really difficult problem with light extraction in light-emitting diodes. And we're going to kind of spend the rest of the lecture just analyzing the physics of this thing. So this is a fun little diagram to really show what's going on here. The left picture just shows like a ray diagram of what's happening. An electron and a hole recombine, a bunch of photons are emitted in every which direction. If they fall inside the escape cone, they can get out. And if they fall outside the escape cone, they just bounce back and forth forever and are eventually reabsorbed. The picture on the right here is actually what you're seeing is an infinite line source radiating electromagnetic field every which way. And this is kind of what a full field picture of the left diagram would look like if you actually solve Maxwell's equations entirely. So it's really cool. I'm really proud of that. It's a fun calculation, so I like to show it off. But it definitely captures the same physics here. So you can see the escape cone right here. That's where light is radiating out here, but everything out here is just kind of bouncing back down and being wasted. So what can we do about that? Well, before we do anything about it, it helps to quantify it a little bit and just see how bad our situation really is. So this is a diagram now from a paper I wrote in 2012, where so the motivation here is you read a lot of textbooks on LEDs and things, and they'll have like a couple of sections where they talk about the light extraction problem, and they just kind of throw a little bit of simplified math at it, but they didn't really analyze it in kind of full detail. So I was working for a startup making infrared LEDs, and these questions kept coming up: is how good can we do really, and what is the physics going on here? And a lot of the references just weren't answering my questions. So I got really fed up and just kind of did all the math myself. And that's what we're about to go through here. So the basic model is you have two regions here, region 1, region 2. Region 1 is my semiconductor LED. Region 2 is my outside environment where I want light to go. And what you do is you model that recombination event of an electron and a hole as a very brief current density, kind of concentrated at a small little point in space. So again, if you've taken 3300, this should hopefully make some sense if you take an advanced DM class. We won't do too much of the deep and dirty physics of it. We'll try and keep it as high level as we can. But the point is, a current density will radiate light. So what I do is I imagine a little surface encompassing that, and I calculate what's called the Poynting vector here. And that represents watts per square meter. So if I integrate that vector around some surface, I can calculate the total power radiating from that little event. So that's what this little integral here is representing. Just some arbitrary surface, and you calculate the surface integral of the power density, total power radiating. I'm going to do an integral on that surface that I can't quite reach in point, but the z equals a surface there. So you notice I'm integrating across infinity. So you imagine this plane here, right? So the event is below, I have this plane, and I'm integrating all the power that breaks that little surface in the z direction across the entire infinite plane, and that is the total light that has escaped from my little radiation event here. Then if I divide by the total power radiated, I have light extraction efficiency. So this is very abstract, but you can start plugging in hard values here in a moment when you give it some simple models. So for example, one of the simplest models is called an isotropic radiator, and it just means it's radiating light equally well in every single direction. It doesn't actually quite exist in nature, but mathematically it's easy to solve, so we might as well give it a shot and see what happens. So turns out, if I imagine a perfect anti-reflective coating, I just imagine all the light that falls inside that escape cone is going to escape, and any light outside of it is trapped forever and reabsorbed. And you just put all that information into that integral, and you can calculate it. And what you find is, for example, so you notice up here, I can use a cursor here. Does that help? So a typical LED might have an index of refraction around 3.5. So that means an escape cone of, say, 15 to 20 degrees, which when you plug into the integral and you find, I get like 1.5%, 1.7, 2% efficiency on my light extraction efficiency. So that's a little concerning because I was already getting like 8% with tungsten filaments. So why would I want to do this with LEDs? Even if everything about this was absolutely perfect, I'm still less efficient than the light bulb. So that's a little unsettling. Fortunately, the reality is not that we have these perfect isotropic radiators. Anytime you have that recombination event, there's a directionality associated with where the photons are going to want to go. So that little current density has some direction associated with it. And the way in which light radiates depends on how this thing is oriented. So if you take like an advanced level EM course, you can actually calculate that directly, and you find that it's this sine squared pattern here. So 0 degrees would be straight up, 90 degrees is to the right or to the left. I'll have the broad side. And what you're basically saying is light that would have gone up or down is sort of being redirected laterally to that current density. So that's kind of cool. There's this, if I can maybe direct my energy up towards that surface, maybe I'll get a little bit more light extraction. So there's our original integral there. And what you do is you convert that thing into polar coordinates, and you weight the power density by this gain factor here, which we just solved for. So it's saying some energy is preferentially going that way, but not that way. And you have this transmittance factor, which if it's an anti-reflective surface, you say it's getting through inside the escape cone, perfectly blocking outside. So it's kind of a windowing function. And you get an integral that you can actually solve pretty well. So instead of integrating across that infinite plane, you notice we're just integrating across the top half of a sphere. So I go from 0 to pi halves, and then from 0 to 2 pi. So all the top half of the sphere. So there's my light extraction efficiency calculation. And you plug it all in, and you get this big, ugly expression. But it's an exact expression you can calculate and graph. So for example, the worst case scenario is if my current density is pointing perpendicularly to the surface, because it's shooting all my energy in the wrong direction, laterally to the boundary, and nothing is actually going up into the escape cone. So that's not a very pleasant situation. Well, but alternatively, if I'm very clever, maybe I could get my electrons and holes to recombine just right so that I'm shooting the energy up into the escape cone rather than laterally into the LED. And again, there's straightforward ways to calculate that stuff. It's just some vector calculus and coordinate transformations, and you get this big, ugly expression here, but it's exact. That's the key thing. You can shove that into MATLAB and graph it, and it's very straightforward. So this is a fun little graph, and you can even look it up here and see all the derivations of that if you really, really get motivated. And what you're seeing are the three cases. So you have the isotropic radiator here in the middle. There's the parallel orientation where I'm broadsiding up into the planar boundary. Then the perpendicular case is over here, and we're calculating light extraction efficiency. This is anti-reflective coating. This is Fresnel reflective if you really want to get fancy, but so you can kind of ignore that for now. Just pay attention to the black curves. And so you notice for every refractive index, there's a corresponding critical angle, so you can kind of see the top and bottom are 1 to 1. And most semiconductors, let's use the cursor here, land right around here, around 2.5 to 3.5 on their index of refraction, which brings you down here about 15 to 20-ish degrees on my critical angle, which even under the absolute best case scenario is 5% light extraction efficiency. So that was a whole lot of calculation just to realize we're not in a very happy place. In principle, I could put maybe a mirror at the back contact, and all that would do is multiply everything by 2. So you notice this only goes up to 50%. That's just because half my energy is going up and half is going down. Anything going down is going to be absorbed forever. But if I stick a mirror there, and in principle, you could just multiply all that by 2. You also notice the limit is I have an index of refraction of 1. Well, there's no boundary anymore, and I get 50% light extraction up, right? That's because half my energy goes up and the other half just goes down. So it's big and it's complicated, but it's consistent and it should make sense. So let's start asking, okay, what can we do with all that light that went in the downward direction? So this is the question, what if we bumpy up the surface? Instead of having a perfectly flat specular reflection with a mirror, I make it bumpy and textured. Now the light isn't going to reflect in perfect angles. It's going to scatter and diffuse in every which way. So remember last time we said that the directivity of a Lambertian profile follows this 4 cosine theta dependence here. And all the energy is going up. And you plug that into the integral and you get actually a pretty simple expression, sine squared of the critical angle. Oops, I hit the button now. There you go. So you see the same principle as I get up to a 90-degree critical angle, actually have 100% light extraction. Because in this case, no light is going down. It's all just going up. So that's kind of our big clue of how we're going to solve our light extraction problem, is I got to do something with the bottom surface here and make it work for me. So this just shows kind of a zoom in where our critical angles are usually around 15 degrees. So you can kind of see 3%, 5%, very terrible numbers here. So let's see what we can do about that. So the only way to really get around this is to make everything bumpy so that when light strikes this surface, instead of being a perfectly specular reflection, I get diffuse scattering. So you can kind of think of that as the rays are sort of distributed among some angular spectrum. And if everything were perfectly flat, then all the rays that fall within the escape cone are exiting and all the rays outside just stay gone forever. But when I have a rough surface, I'm kind of like redistributing the energy in those rays across the angular distribution. So pretty much what you do is you bumpy everything up and you just let the light bounce back and forth a bunch of times until eventually it just kind of finds its way out. The only trick is I need my attenuation here in the meantime to be very, very low. So we're going to do kind of the same calculation we did last time. If you remember Thursday, we went through that big derivation for the Yablonovich limit where you say a ray comes in, I scatter, and I trace the absorption as it goes from one end to the other. And then I calculate how much sort of falls out the bottom and bounces back and forth, and you get this infinite series, which converges into some finite number. We're doing kind of the same thing here. We're not going to quite go through it in the same detail, but it's the same idea of just tracking how much energy do I absorb with each bounce, how much leaves through the surface with each bounce, and then how many bounces does it take before everything's finally settled. So this integral should kind of look familiar. You're asking what is the fraction of total energy that gets absorbed as light goes from, say, top to bottom again. So you notice I have that exponential decay factor here. Here's my Jacobian. Here's my gain profile, probably, because of Lambertian scattering. And I'm doing this integral across the top half of the sphere. So my absorption is basically the transmission minus this is 1 minus the transmission factor here is my absorption, essentially. So this just shows your absorption per bounce depending on your attenuation coefficient, which depends on the nature of your semiconductor. So if I have, say, a very low loss or low poorly absorbing, low attenuation semiconductor, then I could have, say, right here, 100 micron thickness would absorb, say, 30% of the energy as it goes down and back. And if I have a very, very high absorption way up here, I would need hundreds of nanometers before I get there. And if I have 10 microns of thickness, it absorbs like 90% of the energy. So this determines a lot of the overall loss I get per bounce, and it's just a straightforward little calculation to do if you use numerical integration. So now what you do is you ask, okay, I have some light. Maybe it hits the surface here, and it's going to go down and then back again. I absorb some of that as heat or recombination, and then some fraction of that's going to re-escape back out into the environment before the next little bit goes down and back. So the question is, given some energy striking the surface here, what fraction of that energy radiates and how much is going to re-reflect? And that's, again, just some big, ugly integral in spherical coordinates. A very simple way to answer that is just say, what is the ratio of the escape cone to like the total solid angle above me? And it turns out that's a pretty good estimate there as well. But if you want to get really technical, you could solve for all this stuff exactly as well. But that's all that integral really represents. Some fraction of light leaves out into the environment, and the rest is going to bounce back down. And then you repeat that calculation infinitely many times, and it converges actually into a nice, neat little expression, this little eta over eta plus absorption. So you notice as absorption goes to 0, my light extraction efficiency would be 1, and I would have perfect extraction, because light would just bounce back and forth forever, and eventually it just all leaves. But some finite amount is going to be absorbed in the meantime, and that's where you lose some of your efficiency. But you get actually these nice little straightforward curves, and if we go back a little bit, so this is another paper I kind of submitted to a conference on this topic. All the details are there. So what you're seeing here are curves for gallium antimonide, which is a semiconductor we use to make infrared LEDs. And what you're basically seeing is light extraction efficiency is a function of the thickness of my slab. And so I start with some given attenuation coefficient, and as I get thinner and thinner and thinner, my light extraction efficiency eventually approaches 100. So ideally, you can see I want infinitely small thickness. Yeah?
Yeah, I was going to ask, how thin do you make these small?
That's a very difficult question. So at the very least, you need kind of that PN junction there. But there's mechanical limits, is my understanding, to how thin you can really go. So the way this was done is we had a wafer, and I think the wafer that you buy off the shelf is like 400 microns thick. So what they did for us was they took the wafer and put it on a grinding stone, and they just kind of polished it down and down and down. And the guys at the Nano Fabrication Center who were making it said, we're pretty confident we can get you all the way down to about 50 before what happens is it just becomes too fragile and unstable, and it would just shatter to pieces. So that was kind of like we said, okay, yeah, we'll go give it as small as you got. So you look out here around 50 microns, and depending on how you texture it, you're getting upwards of, say, 40, 50% light extraction efficiency. But that depends a lot on how you grow the semiconductor, where it came from, and how you're processing the mechanical limits of the material. But in principle, thinner is very much better. But yeah, there's really no exact answer to how thin you can get, other than just it depends on a lot of factors. So for our particular application, though, we were finding, okay, in principle, we could probably get 40 or 50% light extraction efficiency, which is definitely way better than the 5 to 8% we had with tungsten filaments, right? But you also can see, in principle, if I go just a little bit smaller, I can get up, 60, 80, 90% if I get down to like 10 microns or so. So that's a question for the process engineers in the nanofab, though. All I can say is I'm the optics guy, and all I can say is make it as thin as you possibly can, and I can't really tell you much more beyond that. So if you can figure out ways to make that happen, you can make very efficient LEDs, and then you get rich because you sell them and they're more efficient than everyone else's. So just kind of a side-by-side comparison now. it's fun to just say, okay, we talked about light trapping, then we did light extraction. What are the parallels? How are they similar and how are they different? So in the light trapping world, our goal was get light into a semiconductor. In the light extraction world, we want to get light out. So what we found was anti-reflective coatings are good in both cases. We want to facilitate transmission through that barrier either way. So that was interesting. With light trapping, we found attenuation is our friend. We want high attenuation coefficients so that all those photons get trapped inside our material. Whereas in the light extraction case, attenuation is our enemy. We want as low, little attenuation coefficient as we can possibly get. So it's interesting. Some things are the same, some things are totally opposite. We found thick films are better. So if I had a relatively thick solar cell, that would be great. But a thick LED is bad because it just means light's being reabsorbed that it should be getting out. So I want my LEDs to be thin, and I want my solar cells to be thick. But we also found, incidentally, that thick solar cells can be expensive, so we're forced to make them thin anyway. So there's a lot of give and take and back and forth with the engineering of this stuff. And incidentally, surface roughening was our friend in both cases. So I just kind of like thinking about it. Sometimes some things are the same, some things are totally opposite, depending on your scenario here. So just to kind of close off the lecture, here's another little thought experiment. So remember last time we started with that question of what if I put a bunch of solar concentrators onto my solar cell and do some wacky configuration? Would that be a good idea or a bad idea, practically or economically or physically? So everybody inevitably gets this idea when they do light extraction in LEDs is what if I had like a perfectly spherical LED and I put an anti-reflective coating around it. So now every ray leaving that point is falling inside the escape cone. I have perfect light extraction efficiency. What are some pros and cons to this configuration now? If you want to think about it for a second. And remember, there's not really any right or wrong answer. It's just, what do you think would be the difficulties in making this happen?
Getting that shape.
So yeah, the shape is probably difficult because whenever you do semiconductor processing, everything's in nice, neat, planar stacks. So making a spherical ball of semiconductor is weird. I guess most of the process guys will kind of flinch and do that if you show them this. I guess the next question would be like, where does my PN junction go? I guess you could just sort of split it down the middle or something. I don't know. Because I have to have some N-type and P-type semiconductor in here. Where would my contacts go? I guess I could just have like some positive contacts on the left and negative contacts on the right. Seems like that would kind of work, right? But another interesting question is, what would happen if my recombination event happened a little to the left rather than perfectly in the middle?
Not the focus of the shape.
It what?
And if it doesn't happen in the middle, then this basically just makes the shape a little bit pointless because when you put it in the middle, it maximizes the light extraction.
Yeah, so if I'm off to the left a little bit or the right, some of my rays start falling outside the escape cone again. And they might get like perfectly trapped even if you probably follow them out, which is probably bad. But maybe it'll still kind of work. And I swear I've seen at least a couple of papers where people tried to sort of do something similar to this. But the big question I would always ask is, if you're going through all that trouble, what are you really gaining? Because right now, in principle, if I do really good thinning on my solar or my LED, not my solar cell, and I get it down to say 10 or 20 microns thickness, I'm already at like 60, 80% light extraction efficiency. So will I even be doing better than that? Maybe I'll get 85%, but now it costs 4 times as much. So there's always that little question of, I can already do pretty well, so what's the difference between good enough and perfect if perfect costs me 10 times more to do it, or requires this whole new infrastructure to get around it? Or maybe, where's the problem here is, if this is a flashlight, I need my light to go that way, not this way. So now I need some crazy mirror or something here to focus all my light. Whereas if you notice, if we go way, way, way back, I can kind of get the same thing here. So what they have is this planar thing. There's already kind of a built-in mirror in the back, and there's just a big hemispherical lens over it that already does kind of my focusing for me. So I'm creating more problems possibly than I'm really solving with this situation, right? So maybe it's a good idea, maybe it just creates more trouble than it's worth, but it's an interesting thing to think about because it kind of has that, in principle, it should be absolutely perfect, so why not do that? So again, I like throwing in these little thought experiments because for a big part of my career, a lot of my job was just telling my boss whether or not his ideas are good or bad. Because they'll always sit down, I got this idea, I was in the shower the other day, and what if we just did this thing? And you're like, it seems okay superficially, but, or maybe it is a perfectly brilliant idea if you can figure out all these little issues. So it's always fun to kind of throw these weird curveballs around because sometimes they end up being absolutely brilliant and they work great. And 9 times out of 10, you have to tell your boss, no, that's a bad idea, and here's why. So something to think about because I guarantee you're going to encounter that a lot in your career. So any other questions before we conclude here? Good, you're all experts on light extraction. Yeah?
Instead of polishing down the wafer, would be easier just to drill it on something that's mechanically stable?
Probably.
And you get really thin.
My understanding is that will depend a lot on the material you're using and whether or not you have a good growth process that creates nice crystal lattices. So I know that's how they do amorphous silicon. So if you saw like our last lecture Thursday, we're looking at silicon-based solar cells. When you use crystalline silicon, you get very high efficiency, like 15 to 20%. But when you use amorphous silicon, you can grow it, like you say, you do kind of like a deposition thing, but you lose that crystal structure, which kills some of your efficiency there. So the answer is yes, no, maybe, it depends. If I can be any more vague, but that's actually a common thing. And I think there's probably a swarm of scientists here in the Warnock building and around in the Merrill who are probably thinking of ways to do exactly what you said, to grow material in a way that forms a nice crystal lattice. For example, I mentioned Mike Scarpola on Thursday because his big thing is he's trying to make solar cells out of CZTS, copper, zinc, tin sulfides. And I think a big problem that he's facing is how to grow a decent lattice, crystal lattice, using like a vapor deposition technique. So you have to get your temperatures just right, you have to get all your mixtures of your atoms just right, and your chamber, and your everything has to be all perfectly tuned, and maybe it'll work, maybe it won't. So, but that is, I know it's a thing people dabble with. Yeah. Any other questions? Yeah?
What about cylinders?
Cylinders?
Yeah.
So it's basically this same idea, but a cylinder instead of a sphere. So you still have all those same kind of problems. You're just doing it in a cylindrical geometry instead of spherical.
Connection problems solved.
Maybe. So you're saying you'd have like your top contact and your bottom contact here. Yeah, maybe. That's an interesting thought.
I was maybe your shell would be okay.
Yeah, go run it by the nanofab and see if they can do it. Then, how do I grow a cylinder of gallium arsenide? That's an interesting thought, though. I know it can't be too thick because you have limits to the diffusion of your charge. So it would have to be probably no more than 100 microns thick, if I had to guess. So if it was like 2 feet thick, your charges would just go in like half a centimeter and they all just recombine and you get no light emission, I think is what happens. If I had to guess. I don't know, but that's more of a very deep down on the quantum mechanical level of things, not on the light extraction thing. So from an optical perspective, it might be a great idea, but then on the sort of internal material science perspective, the engineers might go, oh, That's an interesting thought. Sort of a disc-shaped thing. Okay. All right, if there's no more questions, then that's it. Thanks for dropping in.